Yes. So yeah, it's on here. Okay, now it is. All right. Good. I mean, he says it's now. It's okay. So let's go. Uh, all right. So yeah. So what I'm trying to do is I'll try to convince you why there might be some things you might have expected, might not have expected. In any case, some very complicated calculations that I have to justify some way. Right. For people who are not really comfortable with the word Schwinger-Keldysh, although I'll try to make you comfortable a little bit at least, they can just replace that with stochastic. And I have to thank Thomas for the amazing heavy lifting that he did in introducing you guys to stochastics, which means that I can go faster and perhaps all of us can get lunch quicker. Right. Okay, well, in that case, we just stay here and discuss. Okay. So the big picture that perhaps I shouldn't need to say, but I'll say that anyway, that effective field theories are amazing. They allow us to describe very complicated many body systems with fewer ingredients that are probably more tangible, more usable, and whatnot. But the textbook, I mean, the quantum field theory or effective field theory that you really learn in your undergraduate courses or perhaps even in postgraduate courses is not really suited for non-equilibrium systems. It's either suited for zero temperature systems, which is perhaps most of quantum field theory that we study, or it is suited for thermal systems. Uh, Maybe you had a course in statistical field theory or Euclidean field theory, so that is that. If you want to go out of equilibrium, your options, I mean, there are many options, but they become slightly more cumbersome. And perhaps the best of these options, which is the reason why we are here, is hydrodynamics, because it provides a universal framework to systematically study systems that are not arbitrarily out of equilibrium, but still sufficiently close to equilibrium. So that's what we're going to talk about here. Now, in some sense, classical hydrodynamics is very much like an EFT. I mean, after all, there are fields. You have velocity, temperature, density fields, which are locally varying. So by that context, it has to be a field theory. But it's not really a field theory in the very strong sense of the word, because normally when you write down hydrodynamics, you start with constitutive relations or conservation equations and not with an effective action. And that is what I would mean in this talk to be an effective field theory. Uh, just a disclaimer that this has, of course, changed in the recent years, which is why I'm giving this talk, and I'll try to say more about it as we go. Right. So the reason why we might even be interested in talking about an effective field theory version of hydrodynamics is that a lot of us know that hydrodynamics by itself is not complete. It includes dissipation, as was pointed out, but not fluctuations. And you need both of them to be compatible with fluctuation dissipation theorems. If you don't know what that is, that's fine. Just trust me, you need fluctuations. And Schwinger-Keldysh hydrodynamics, just like stochastic hydrodynamics that Thomas was talking about, is in a sense an EFT extension of classical hydrodynamics that allows you to systematically incorporate thermal fluctuations, but more importantly for me, starting from an effective action principle, so that I can bona fide treat this as an effective field theory and use a lot of technology that is at my disposal, right? So here is my broad context diagram. Here above, we have hydrodynamics. It has all the nice things. It is based on conservation laws. It can be used to describe non-equilibrium dynamics close to equilibrium. But as I said, it includes dissipation, but not fluctuations. So it's not compatible with FDT. Stochastic hydrodynamics is a step further. It includes fluctuations. You do have tree-level FDT. So you introduce fluctuations by demanding that your FDT is correct at the tree level, but it may violate it at loop levels, for which you have to do complicated checks. Uh, it does not include nonlinear stochastic noise, at least from the get-go, but you can do many extensions like non-Gaussian noise and multiplicative noise and whatnot. And of course, it doesn't have an effective action principle. And these final 2 points are things that you would not want to address and are addressed by Schwinger-Keldysh hydrodynamics, which is that it has an action principle now, And it has a nonlinear symmetry known as the KMS symmetry, which makes sure that FDT is satisfied at all loop levels, which is dictated precisely by this symmetry. So this is one of the two binding reasons, in addition to just being fundamentally nice, that I would want to work in the Schwinger-Keldysh hydrodynamics framework. Now, there's another side of the story that, of course, here I'm talking about an EFT, which I want for hydrodynamics. There is a field theory, the statistical field theory that we already know. As I said, like at finite temperature in equilibrium, we know how to describe systems with an effective field theory, which is the statistical field theory. It checks out a lot of things that you would want. It governs equilibrium configurations. As the name suggests, it has an equilibrium effective action, or rather a free energy that it is based upon. It includes equilibrium fluctuations, not really non-equilibrium fluctuations, but of course that cannot be used directly to obtain dynamics. And what I would want in this talk to sort of think about the connections between these two, like, can this field theory, which is supposed to be a broader field theory, does it encompass within it the statistical field theory, at least in some non-trivial checks? Okay, so the rest of my talk will be about first describing to you in a little bit more detail what I mean by hydrostatic compatibility in precise terms. Then I'll give you a little bit of introduction to Schwinger-Keldysh hydrodynamics. I'm just going to get this cursor out of my way because it's annoying me. It. Then I'll, okay, that didn't work. Sorry. Uh, okay, yeah. So then I'll talk about a little bit of introduction to Schwinger-Keldysh hydrodynamics. Once I have those two ingredients, I want to tell you a little bit about hydrostatic compatibility at one loop order and stochastic fluctuations. And my gut tells me that that's all the time that I'll have. But in case my gut is wrong, then I'll be able to tell you a bit about BRST ghosts and what they have to do with the story. And in the end, I'll try to at least tell you some lessons that I have learned and you might find interesting in the story. Good. So your hydrodynamics 101. Hydrodynamics is a theory of conserved charges, conserved variables that can survive over long distance and time scales. And that is why, in some sense, you expect them to govern the low energy behavior of your many body systems. For the most of my talk, actually for all of my talk, I'll only talk about a single variable, which I dictate, say psi, and it is conserved. So it has this conservation equation. A lot of what I say can be extended to momentum variables or other variables, but I'm going to keep my life as simple as I can. Now this equation can be used to determine the dynamics of my field psi, by which I mean that if I give psi to you at some initial time, then you can use this equation to evolve this and tell me psi at all times. But to do that, you need to tell me what this J is. So you need to express J in terms of psi, which are known as the constitutive relations of hydrodynamics, thematically speaking. Here I have two terms. One of them is the diffusion term, which tells you how J changes by changes in psi, the spatial change gradients of psi. Then there is an electric field response, which is that if you apply an external electric field, how does your current respond? And what happens is that there is a relation between this coefficient here, which is known as the diffusion coefficient, and the conductivity coefficient here. They're basically related by susceptibility, which is the first derivative of chemical potential with respect to the field. Now, I am not going to tell you where this comes from, but in hydrodynamics, this basically comes as a consequence of the second law of thermodynamics. If you demand that there is a local entropy production at every point in space and time, then this is what comes out of it, in addition to the fact that this conductivity coefficient has to be positive. But all in all, this tells you that the constitutive relations take this particular form. Now, you don't have to remember this because I'm not going to use this. I'm only going to use the fact that there is a relation like that. And in general, there are relations like that in hydrodynamics, which are sometimes called equality constraints arising from the second law of thermodynamics. I'll call them hydrostatic compatibility relations. They're essentially relations which tell you that hydrodynamics has to be compatible with thermal equilibrium. This is precisely what I mean by this, that in presence of time-independent background sources, which means if I go back and I take this H to be time independent, or rather electric field to be time independent, then in the presence of time independent sources, hydrodynamic equations must admit a time independent equilibrium solution. Furthermore, that equilibrium solution must be governed by an equilibrium generating functional. So this is my generating functional. It is given by some path integral over equilibrium configurations of my field, let's say order parameter, and there's a free energy, and then there's a coupling term. Right? That's, I mean, to be honest, I mean, it is in these papers that I think it was first formalized a bit more properly in the context of hydrodynamics. And partition function is much more powerful than this, the generating functional. It also tells you that you can get all the constitutive relations in equilibrium also from the generating functional. But for me, this is all I really need. This is my definition of hydrostatic compatibility, at least for classical hydrodynamics. And you can quickly check that this actually works out because the generating functional is dominated by the saddle point where the chemical potential is equal to H. Chemical potential is the variation of F with respect to psi. And then if you plug this in, you will find that this becomes a solution of your equations of motion if and only if this factor here is 0, which was precisely the hydrostatic compatibility constraint. And this continues to hold. All equality type relations that come from the second law of thermodynamics actually can also be seen as hydrostatic compatibility relations. So they tell you that there must be a generating functional, equilibrium generating functional that dictates those configurations. No, so this, so here this X, bold X is supposed to be mean that it's only, so it's only integral over space directions. And I am performing a path integral only over time independent configuration. That's what this equilibrium here is supposed to mean. Yeah. It should be. So, I mean, at any order in gradients, I would expect that there is some free energy which is appropriately corrected with gradients such that this should be true. So this is more like a postulate. I would demand that for my hydrodynamic theory to be consistent at any order in derivatives, there must be a free energy at that particular order in derivatives for which this statement is true. Yeah. All right. Yes. Uh, I really didn't want to go into this, but I'll give you a one-line answer. Okay, maybe I won't give you a one-line answer. Okay, so the second law constraints come into two classes. One of them are equality constraints, one of them are inequality constraints. Inequality constraints are true non-hydrostatic constraints. They really tell you that entropy has to be produced. But the hydrostatic constraints, I mean the equilibrium, the equality constraints, essentially arise from the fact that the dissipation has to vanish as you go in equilibrium, and which is precisely the relation that relates those constraints with this thing, that at the end of the day they are asking the same thing, that when you go to equilibrium all the dissipative effects vanish, and that's why you must be dictated by some generating function of this form. I'll give you a more detailed answer if you want after the talk. All right. So what I'm going to do is I'm going to change a bit of gears, and I'm going to do work with a slight generalization of my hydrodynamic model and make it not technically hydrodynamic. I will take this equation of motion, which Thomas also showed. It's essentially an equation for the evolution of psi with some operator gamma. Mu is again the chemical potential, and H is the background field. If gamma was exactly this derivative operator, then this is precisely the diffusion model I was showing you just now, also called model B in the Hohenberg-Halperin classification. If this was just a function of psi, not a derivative operator, then this is called model A because psi is no longer conserved. But technically speaking, only model B is hydrodynamic, but a lot of things are much more simplified in model A, so I'm going to keep that to make my calculations tractable. For concreteness, I will use the free energy to have the standard form. It has a kinetic term, or rather the gradient term, and some potential, which I'll take to be this. In general, you can have higher order terms as well. This gives rise to a chemical potential, which has a linear susceptibility term, and then again nonlinear terms. And similarly, I will have expansions for these gamma and sigma coefficients. Yes. Uh, I will have something to say about phase transitions at the very end. I'm not really interested in phase transitions right now as such. So then the point about order parameter does not really make all that sense. The only thing I'm really interested in that there is some variable psi, could be an order parameter of the theory that you're interested in or whatever. Somebody came to me and told me that I want to describe the dynamics of this psi and gave me this equation, and I want to sort of think about what the properties of this equation. But it would be the order parameter if you were interested in critical dynamics. So in particular, if this A2 vanishes, then this model precisely goes to the critical point, as Thomas was mentioning. And then, yes, I am describing, if I work around that point, then I am indeed describing dynamics of the order parameter. Yeah. Okay. Good. So what can I do with this model? I mean, of course, I just said that I can determine classical evolution of psi with this model, but I can do some more things that I will do in this talk, is that you can use hydrodynamic equations to compute the classical retarded correlation functions, also called response functions. We basically take psi on shell, which is the solution of that equation. You vary it with respect to h, and that's what you call the response function. Right, in model A and model B, this is the typical form that these response functions take. They will always have a pole, a retarded pole, which means a pole in the lower half complex omega plane, and they will have some numerator, which is dictated by some dissipation. And the fluctuation dissipation theorem essentially tells you that this numerator is somehow related to this pole in the denominator, which you can already see. Right. Now, what you can do on the other hand with the free generating functional is that you can compute the static response function, which is essentially two derivatives of z equilibrium with respect to h. If you truncate it at tree level, remember I said that partition function also knows about a bit about equilibrium fluctuations. If you truncated this expression at tree level, because z in general, this is a statistical field theory, so it has interactions as well. If you ignore that, then you get the classical equilibrium function, which is just the equilibrium value of psi, and you vary it with respect to h. And this is what you get. And the hydrostatic compatibility, where remember I told you that the psi on shell, when it becomes time independent, should become the psi equilibrium, by definition means that these two objects have to agree when frequency is 0. So the retarded function as omega goes to 0 must be the same object as the equilibrium function that you obtained using the partition function. And this is my hydrostatic compatibility at classical level. And this will be true if my previous expression about hydrostatic compatibility was correct. Now, what I want to do is I want to go a bit further, because this guy has loop corrections, of course. As I said, this is a bona fide field theory. So I want to ask the question whether this expression here also holds true in the presence of interactions. This is pretty much the question that Pavel was just asking Thomas, that what happens because you were fixing fluctuation dissipation theorems at tree level, what happens in the presence of stochastic interactions. I'm not going to answer that question. I'm going to only answer that question, or try to answer that question, order by order in interactions in a field theory. And I want to ask whether this holds true at one loop level. That's all I can really do with my limited capabilities right now. Now, the right-hand side of this expression, the G equilibrium of K, you can systematically compute it using your favorite field theory tools. This is your free energy. It has two interactions. And you can convince yourself that there are these two diagrams that will contribute at one loop level to this G equilibrium K. I'm not going to do the courtesy of writing out what the answer is, but you can trust me that you can compute this answer. And I want to see whether whatever that answer is, can I also reproduce this using the left-hand side. Now, left-hand side is now trickier, because so far my hydrodynamic theory gives you no prescription whatsoever to compute those loop corrections. And to do that, you need either stochastic hydrodynamics, or what I'll do is Schwinger-Keldysh hydrodynamics. And the big question of this talk will be, is Schwinger-Keldysh hydrodynamics compatible with hydrostatics? The answer would be depends, and the rest of the talk will be about depends on what. Yeah. Right. 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 Sorry, you will have to repeat the last part of your question. Yes. Yeah. Right. Uh, so in terms of finite temperature field theory, especially in the Matsubara formalism, in imaginary time formalism, you get the imaginary time propagator. And the imaginary time propagator is, of course, dependent on Matsubara frequencies, not real frequencies. So this object here, G equilibrium, is the Matsubara propagator at omega goes to 0. Yes. So, I mean, this is right. I mean, so essentially, Matsubara formalism gives you imaginary time propagators. Schwinger-Keldysh or some other, this two contour theories will give you the real time, and they have to agree on omega equals to 0. Exactly. Yes. Yes. But I mean, that would be, you can pose it in that language if you knew what your microscopic theory is, because you can take that microscopic theory, put it on a Schwinger-Keldysh contour, and you can explicitly compute these objects, and they have to agree by definition. Here, because we are doing effective field theories, we have to work harder, and we have to make sure that this is true as a compatibility condition, right? Okay, good. So back to depends on what. Before doing that, let me just tell you a bit about what I mean by Schwinger-Keldysh hydrodynamics. This in no way is going to be complete because I don't think I could do that, but I'll at least try to introduce the ingredients that I will need in this talk. Uh, so what do I need? Now, so the point, as I mentioned before, is that there are fluctuation dissipation relations, which mean that hydrodynamics, at least the classical one, is not complete. You need fluctuations. So this is what the fluctuation dissipation theorem looks like. I have taken temperature to be 1, which I'll continue to do in the rest of this talk. The left-hand side of this expression is essentially the variance of whatever variable that you're interested in. Is essentially psi square expectation minus the square of the psi expectation. The right-hand side, the imaginary part of G retarded, heuristically speaking, you can think of it as how psi decays as time goes on. And this dictates what the dissipation is, and the left-hand side dictates what the fluctuation is. And these two things go hand in hand. You cannot have one without the other. Whereas in hydrodynamics, you do have one without the other. You have this object here, but you don't really talk about any sort of variances whatsoever. Now you can fix that by introducing stochastic fluctuations. So this is what the symmetric correlation function actually computes. And this is what you're going to do just now. But the more interesting thing for me is that once you introduce stochastic fluctuations, they can back react on the retarded functions. So the tree level retarded function that the hydrodynamics actually computes is not correct. This symmetric correlation function, so stochastic fluctuations will back react on the retarded functions and give loop corrections, which is the thing that I'm really interested in. And Schwinger-Keldysh hydrodynamics, I'll only predominantly use it as a tool to do this in a bit more systematic manner that I am comfortable with. All right. Before I do that, let me just give you this quick slide for people who might know this. If you don't, you're probably not going to learn anything from this. You can write down stochastic hydrodynamics. This is what we had in the previous talk by taking the classical hydrodynamic equations and adding to it a noise component with some factor here. The reason I have a factor here is because I'm taking this noise to be pure Gaussian, which means that it has zero expectation value and a constant width, which means that all information about the physical width of the noise is in there in that function that sits at the front, and it depends on your variable in general. Another way, so now that you have this, you can compute actual expectation values by taking whatever you want, taking it on shell in the presence of theta, and then summing over a Gaussian probability distribution with that theta. And that's it. That's what you would do to compute these variances in stochastic hydrodynamics. This multiplicative factor f is actually fixed to square root gamma u2 fdt. This is also what we saw in the previous talk. I'm going to use a bit of Schwinger-Keldysh notation moving forward. So psi that I had previously is essentially the expectation value of psi r when I sum over all noise fields. And h, I'm going to just define it to be hr. This is something that you do in Schwinger-Keldysh. I'm not going to tell you why, but that's that. Now, if you have that, then you can write down a shortcut to compute these correlation functions, which is the Schwinger-Keldysh or MSR generating functional, which is this object here. You compute, I mean, essentially, this the same object here. All I've done is I've introduced a new source HA that couples to the field psi so that you can compute expectation values of psi. And I've introduced a delta function which makes sure that the equations of motion are imposed. So you can convince yourself that if I vary this object with respect to HR, you will pretty much, HA, you will get pretty much exactly the same object here. And once I have that, I can write down these shortcut methods. My retarded function is essentially one derivative with respect to A, one with respect to R of this object. And the symmetric function is just two derivatives with respect to A. So this is something that I will use. So I just want you to be convinced that knowing this object is sufficient to tell me about retarded and symmetric function. Sorry. Yes, I do. And good spot. I'm going to bring it back. No, yeah. So this is yeah. So you are way ahead of me. So yes, I will put the Jacobian, but I'll put it a bit later. So this is what you would, because once you put Jacobian, you need to introduce some ghost fields to actually exponentiate the Jacobian, which is the BRST ghost pass of the talk that I wanted to talk about at the end. Okay, modulo that, let's say this is the object that computes this. And then I can do a bit of algebra. I can take this delta function and introduce a Lagrange multiplier to impose this equation of motion. And having done that, I can integrate out this theta because this theta is purely Gaussian. And this is an action that I get. This is the MSR effective action. It's a kind of Schwinger-Keldysh action, but not necessarily. But it's an action that you can use to compute these objects that I'm interested in. I'm going to go and do it a bit more generally by classifying what properties this generating functional should have. So this is generating functional. These are the objects that I'm interested in that I can compute using the generating functional. Generating functional, I mean, of course, we know hydrodynamics is not a unitary theory. It has a separation, but it has to emerge out of some unitary theory that underlies in the microscopics. These are the three conditions, which I'm not going to explain where they come from, but these are the three conditions. One of them is that when the A-type source goes to 0, the partition function should normalize to 1. There are two more, but whatever they are, they make sure that the retarded correlation function only has poles that lie in the lower half complex omega plane. It's a very important property because this function actually computes a response. And if this was not true, then the real-time one will not be proportional to the theta function, which is very important because you cannot expect a response before you have made a perturbation. So the theta function makes sure that you perform a perturbation, and only after that point in time, you will see a nonlinear response. And this has to be true arbitrary order in loops. And then another thing that this object here does, it makes sure that the symmetric function is positive definite. Remember that the symmetric function computes the variance of a variable, and variance by definition has to be positive. So these are at least, I mean, there's a lot to do with this, but at least these are the two properties that I'm going to use at this talk. And then there's this infamous Kubo-Martin-Schwinger symmetry that I just mentioned before, which makes sure, I mean, some symmetry, some discrete symmetry, which I won't really go into more, but it makes sure that the fluctuation dispersion theorem is satisfied. Yes. Right. Mm-hmm. Mm-hmm. I think the question here is like, so this object here, I'm only really talking about, these are response functions. So response functions are to be computed on top of a state. And these are computed on top of the thermal state. So I start with the thermal state, I do small perturbations, and I demand that those small perturbations satisfy this relation. And KMS will be satisfied as long as you are doing perturbations on top of the thermal state. If your state itself is something different, some complicated hydrodynamic flow state or whatever, and then I do perturbations on top of that state, then this is not necessarily satisfied. But as long as my state of interest is equilibrium and I'm only doing fluctuations on top of that state, this has to be. Yeah, I think another way to think of it as microscopic reversibility, which is, I think, pretty much what Thomas was converging to, is that you can make this exact statement in terms of some statement about microscopic reversibility, which is that the response functions and the response functions of the time reverse theory have to be in a particular, have to satisfy a particular relation. And this is, and then that is a purely dynamic, and that doesn't depend on a state, because right now I'm making a statement about response functions. That is not a statement about response functions. Then it becomes a pure statement. And then essentially the only ingredient that goes in is that the state that you're interested in, again, like I would say that the state that you're interested in. So when, I mean, so what are these correlation functions? That trace rho something. As long as that rho that sits in there is a thermal rho, this becomes an identity. Right? They imposed my equation of motion. So there was this delta function here to impose this equation of motion, and that Lagrange multiplier introduced imposes that equation of motion. No, no, no. Okay, good. So this is just general properties of generating functional that you can prove in general for any theory. So let's go ahead and talk about Schwinger-Keldysh effective field theories, which will essentially, we are trying to construct these generating functionals from some microscopic or some effective field theory business. So what I mean by that is I want to introduce some degrees of freedom, and I want to integrate over those degrees of freedom an action that is given in terms of these background fields as well as these dynamical fields. Just by the way, this psi could be different than psi. This will become important in just a minute, but right now they can be just, I want to introduce some fields and some effective action such that this generating function has all the right properties. Now, these are the three unitarity properties that I wanted, and it turns out that they become these three properties of the effective action. Uh, More importantly, the imaginary part of the action has to be positive. There is some normalization condition and there is some reflectivity condition. And similarly, the KMS condition becomes not only it acts on the background fields, it also acts appropriately on the dynamical fields, and the full action has to be invented into this combination. Right? Some leap of faith there. Now, why I call it a leap of faith is that just keep in mind this equation because this will become rather important. This condition about normalization that Z as all sources go to zero, all A type sources go to zero should be one. Technically, this the top implies the bottom doesn't imply the top, which will become important just in a second. So here is what a Schwinger-Keldysh effective field theory for the model A and B that I'm interested in would typically look like. One very important thing that almost, I mean, everyone knows, right? I mean, a classical system of equations does not uniquely determine what its field theory version is going to be. There can be multiple field theories that have the same classical dynamics. And the same is true for Schwinger-Keldysh effective field theories as well. You can have multiple Schwinger-Keldysh effective field theories that actually boil down to the same classical dynamics in when you actually compute the equation of motion by variations. What these ingredients are not very important. The only important thing that I want to point out is that these are two actions which satisfy all the postulates of Schwinger-Keldysh EFTs that I just said. They also both realize a KMS symmetry, and the only difference between them is that they are related to each other by some non-trivial field definitions. So you perform some non-trivial field definitions between some variables, and you will find one in terms of the other. But in general, these two field theories as field theories are different, right? There's a bit of comment to make about these KMS symmetries also being distinct, but let's skip that. Yeah, yeah, I meant to make a comment about that. Why I call them canonical and grand canonical, that's purely my terminology, so it's not standard in any sense. Why I call them canonical is that on the left hand side, I'm using psi directly as a degree of freedom, which is the variable that I'm interested in. On the right hand side, on the other hand, I use this very funny variable phi, which is related to the chemical potential directly rather than psi. So it's only in that very naive sense that I call them canonical and grand canonical, is that the effective degree of freedom in this field theory is related to the chemical potential directly rather than the grand canonical variable psi, or rather the actual variable psi. Sorry? Right, right, right. Yeah, yeah, in that sense, yes. So yeah, so of course, as I said, like they are related by non-trivial field definitions, the two sides of the theory. And so in a classical description, it doesn't matter which one you use, but in a fully field theoretic description, it does matter, because when you perform such field definitions, generally there's a Jacobian associated with that field definition. That means which will change the renormalization structure of physical observables. So there will be some non-ellipticities that will remain the same, but any renormalization that you get will crucially depend on what degrees of freedom you use. Which brings to my lesson from here is that at least one of these schemes will be incompatible with hydrostatics, because if I start from the free energy, I get an unambiguous answer from for that free energy for the fully cut-off dependent renormalization of all coefficients whatsoever. Whereas here, depending on the field description that I use, I will get different cut-off dependent terms. So which means that I have to make up my mind which one to use. And the one to use is the one that will give me the correct renormalization of my hydrostatic coefficients. And a priori, either one or both of them could be wrong. Maybe there's a third one which is correct. Sorry? What is wrong? Sorry. Yeah, okay. Sorry. I think, yeah, maybe my grammar skills are not as good as I pretend. But okay, I mean, I say may because it could be that for the observable that you're interested in, the the regularization actually turns out to be the same. There is, I mean, at least at this point, I don't have anything. But yeah, you're right that I should really say, I mean, what I really wanted to say was that at least one of them will be wrong. Right. Uh, yeah, yeah, yeah. I think I do, but I let's talk about that more. Yeah. Maybe when I have said what I wanted to say, you could clarify in this language what my question would be. So why I say that? Yeah. So I mean, so I don't have enough information on this slide for you to convince you, to be honest. But why I expect that is that because if I compute, let's say, a 2-point function from the left theory at one loop and from the right theory from the one loop at one loop, the two answers might differ from each other with some cut-off dependent terms. Precisely because technically I should have performed a field definition more carefully with some determinant and with those ghosts, and those ghosts will contribute some cut-off dependent terms in my theory. So I would expect that if I just use the left or the right, my answers would generally be different from each other with some sort of dependent terms. Right. Yeah, yeah. Yes, yes, yes. Yeah, so maybe I'm not seeing your point. Both, you will get an answer from both sides, and both the answers, so I mean, you will get an answer for the symmetric function from here, for the retarded function from here, which will be compatible with with FDT. Similarly, you will get an answer for symmetric and retarded on the right hand side. They will be compatible with FDT. It's just that the two answers will not necessarily be the same. Right. No, this I think that is precisely so. The re the correlation function that I will compute is by varying this object with respect to HA. So the correlation function I'm computing is always of this physical object psi r, which is also when I compute this with respect to HA, I get the correlation function of this operator psi. So for instance, if I were to do this for current, I am computing the correlation functions on both sides of the same object, classically the same object, related to each other by field definitions. So it will be the same current, but on the different sides, it will be expressed in terms of different variables. And I will get I mean, classically, the answer will be the same because there are no interactions. But when you introduce interactions, the answers will be different. Yes. Yeah, you will have different when you compute the loop correction. I mean, I'll give you the answer. You can tell me if it is wrong, but okay. Coming to your answer, I'll give you the results for one loop order, hydrostatic compatibility at one loop order. So these are the Feynman rules that I'm going to use. If you have seen this, good. If you haven't seen this, you're not going to learn it from here. In general, these are the two lines. One, the solid line represents my physical field. The squiggly line represents my noise field. The noise propagator is always zero in these Schwinger-Keldysh kind of theories. The mixed propagator is purely retarded. It only has pole in the lower half complex omega plane. The solid propagator or the symmetric propagator has one pole in the upper half plane and one pole in the lower half plane. The general structure of these theories. There are interactions. There are interactions which only have one noise field in them, and then there are interactions which have two noise fields in them. And you take, I mean, I haven't written down their Feynman rules, but you can compute them quite easily. And you basically go and do your field theory with these ingredients. Those are propagators, those are your interactions. And what you find is that if you don't do any loop calculation at tree level, this will reproduce exactly the answers that you expect, not just for two-point functions, but all three, four, high point functions. I want to do loops, right? So, okay, I probably am not going to as great on time, but if you start doing loops, you immediately run into a very big problem. And the problem is that the answers you get are completely garbage. Because there are some diagrams that would contribute to the retarded two-point function. So these are those diagrams that contribute to the retarded two-point function with the ingredients that I gave you here, which are like interactions with one and two noise legs. And you can see that these are the two diagrams that you can compute, and they will contribute to the retarded function. But they have a very problematic thing is that this leg here has a pole both in the upper half and lower half complex omega plane, as I just said, whereas this one only has one in the lower half plane, which means that the actual computation will not have poles exclusively in the lower half complex omega plane. And as I said, this is a very, very big problem, which means that the response function does not behave as you would expect it to behave. And what went wrong was that thing that I told you, that while this property implies this at free level, this by itself is not sufficient to ensure that your full generating functional has the correct normalization beyond free level. Now, there are various fixes that you can do to this. The fix that was pretty elegant and came up in this paper by Hong Liu and collaborators, which I'll call the GGL prescription, it sort of prescribes that rather than using the original theory, let me just modify my classical hydrodynamic theory by doing some fancy regularization and introducing some new poles in my theory. Whatever that is, it modifies the propagator within this particular form. And once you do that, basically what happens is that this propagator now has a lot of poles in the lower half plane. And when you compute loops like this, you can see that these loops are always purely retarded, and which means that when you compute these loop diagrams like that with this appropriate regularization for large enough P, they all vanish. So you throw away all problematic things, and this was shown to well, at the level of full partition function in this paper. Goldstone field? Yes. Yeah, I'll do that next. Yeah. So, I mean, of course, that was originally what you would have done, but this was a quick fix. And I just want to make a small comment about this quick fix is that while this quick fix is something that gets rid of this problem, it creates another problem, which you may or may not be think very problematic, is that once you do that and you impose the KMS symmetry, you find that the imaginary part of the action is no longer strictly positive. So, which, as I said, is very important to make sure that the symmetric functions have the correct sign positivity. Now, I say this with a grain of salt. Why? Because this is all only really relevant at large omegas. At small omega, of course, these terms are much smaller than the leading term. So in the regime that you're interested in, everything is fine. It's only when you introduce more and more, I mean, you go outside the regime of applicability of hydrodynamics that you will start seeing problems, which you may or may not be interested in. You might imagine that at least theoretically speaking, there will be some regularization that will fix this. But modulo that, there is this problem that you may or may not worry about. Just a side comment, similar problems also appear when you try to write down a Schwinger-Keldysh or effective MSR, effective action theory for relativistic hydrodynamics in what is known as the BDNK frame. May have had discussions about this. I don't have the time to go into that, but in case you're curious. All right, once you do that, you can employ the GGL prescription, and these are the diagrams other than the two problematic diagrams that I just showed. The above two diagrams also vanish in GGL prescription because they also have a purely retarded loop. Only surviving diagrams are these three, which you can now go back and actually compute. The computation is hard. So the first computation that you could do is you could throw away all cutoff dependent terms and only look at non-analytic contributions that come from this calculation. And in model A, there are no non-analytic contributions that come. So that is that. But at one loop level in model B, there is a non-analytic contribution, which is this famous long time tails. So there is a square root, which the square root means that if in the limit that k goes to 0, this will give you omega to the power 1/2, which is the well-known long time tails. It tells you that the hydrodynamic modes decay polynomially at late times rather than exponentially. And one weak version of hydrostatic compatibility could be that because we know that at the end of the day, this answer has to match with some hydrostatics which come from a free energy, which is an analytic expression in momentum. So which means that all such non-analytic behavior should vanish as omega goes to 0. And this, I mean, you trivially see that does happen in this case. There's an omega in front. So as you take frequency to 0, this non-analytic piece vanishes, and your retarded function is analytic in the limit k goes to 0. In the limit omega goes to 0, it's an analytic function of k. So this was something that we worked out some time ago, and that's fine. So the second more ambitious question I want to ask is what happens if you do the full cutoff dependent calculation. Now there's nothing that you will learn from this statement because it's quite complicated, but I'm quite proud of this because I have managed to do this after several months of calculations. But here is that. This is the full cutoff dependent hydrostatic compatible result. So the result that you would expect out of your calculation for model A and model B. You can play with this and actually find the correct renormalization for diffusion and conductivity using this, which I am not going to explain. But if you take these expressions and you set omega to 0, you will find an expression that is given just in terms of k. And this expression only depends on hydrostatic coefficients, the free coefficients that appear in the free energy, and you can check that this is exactly what you would get from a hydrostatic computation of these two loops. Now, why am I talking about this? Is that if you actually do this calculation in Schwinger-Keldysh with the GGL prescription, you do not actually find this result that I've just mentioned above. You do find it in this canonical scheme in model A. It does work out, and you have exactly the same answer as you would expect. But in the grand canonical scheme, you get a residual contribution, which is not correct. Similarly, in model B, the canonical scheme, by the way, I did not mention this, the canonical scheme is actually not applicable. I have to go very back, I was avoiding this. There's a 1 over gamma here, which means that since gamma is a differential operator in model B, model this canonical scheme does not really apply to model B. So for model B, you only have the option to do the grand canonical scheme. And lo and behold, so this doesn't even apply. So for model B, you have the problem is much more serious because there's only this grand canonical scheme that is applicable, and even that scheme does not give you the right answer. So in case you're already asleep, here are the things that I wanted to say is that fluctuations introduce loop corrections in retarded functions and can be computed using Schwinger-Keldysh hydrodynamics. The naive Schwinger-Keldysh results are incorrect because of non-unitary diagrams, but you can fix this using a clever regularization prescription. Then there can be multiple Schwinger-Keldysh EFTs in the first place for the same classical hydrodynamic model, and depending on which one you use, you get different results for hydrostatic compatibility. In the canonical scheme, which applies to model A, everything works out. But in the grand canonical scheme, which applies both to model A and B, neither of those work. Right? Okay, in the final bit of time that I do have, I'll tell you about BRST ghosts that have been teased quite a bit. And at least in this context, the reason why you would want to do that is precisely the problem that I just said, is that the GGL prescription gives you the correct results in the canonical, but not in the grand canonical scheme. Which means that for model B, for which only the grand canonical scheme applies, you really don't have any option, and GGL does not give you the correct hydrostatic compatible result. And actually, the proper way to do this is something that people had figured out before the GGL thing was introduced, was that you have to introduce BRST ghost fields that will systematically cancel all unphysical contributions. Now, in MSR, this is precisely done because of this factor that I very advertently removed, which is that if you were to define this generating function, not only do you have this delta function to impose the equation of motion, you should also have a determinant, functional determinant for this equation of motion when you vary it with respect to the degree of freedom that you're interested in. And this object here, you can exponentiate by introducing BRST ghost fields. These are the CR and CA, and you can exponentiate it in the usual Faddeev-Popov way. And these are the ghost parts of the theory that you were talking about. Yes. I'll give you an answer. I'm not sure if that answer is what you're looking for, but the point was that I wanted to impose this equation of motion on this field psi, right? And to do that, you have to put in a delta function. And now the delta function, so normally you have this delta function, but generally when you do this for delta functions, you have to also be very careful about what are you integrating this delta function over. So if this delta function was a linear function of psi, then this determinant will be 1 and nothing would matter. But if, let's say, this delta function has a non-linear term in psi, then you need a functional determinant to properly define this delta function integral. So it's a no, Lagrange multiplier will come next, because Lagrange multiplier will come when you take this delta function and exponentiate it into, it's one step before. So it's even before you go to the delta function, you need to have that functional determinant. Right, and this, and the, yeah. Which symmetry are you talking about? Sorry. Which symmetry is unbroken? Right. Right. Uh, Again, I'll give you an answer to this. Like if I do this for model A and B, the models that I'm actually interested in right now, you will find that the BRST symmetry is just there. You can check that BRST symmetry is there. Yeah. Yeah. Yeah, I wouldn't be able to give you an answer for that. Like I don't know if it is spontaneously broken or not. Here, yeah, no. Sorry. All right. So anyway, as I just said, so BRST symmetry is basically just a consequence of this procedure that I did there, and it ensures that this property that I was interested in actually follows uh, from this symmetry. The problematic part is that if you use this prescription to introduce ghost fields in your theory by using this functional determinant, then it is not guaranteed that this ghost sector will furnish a KMS symmetry, which this one does. This one will generally not furnish a KMS symmetry, so which means that your ghost sector might violate KMS. That's also problematic because then your ghost sector will violate FDTs. Uh, Another point to make is that here I use psi as a degree of freedom. If I instead used phi, which is related to the chemical potential like this, the determinant changes. So the Jacobian changes and this ghost sector changes. So the ghost sector is sensitive very much to what degree of freedom you're using. And that is as we expect, because in the end, we would expect the same physical answers and the two choice of degrees of freedom should be different from each other, at least in the ghost sector. Uh, so, y- so what? So it depends on what you demand, right? If you demand fluctuation dissipation theorem at tree level, that is not sufficient to dictate a KMS symmetry, right? Because a KMS symmetry will imply fluctuation dissipation theorem non-perturbatively because it's a symmetry. And what would happen is that if you introduce ghosts in this method, I mean, we can discuss, there are counter examples that we worked out, that if you do this in for an arbitrary theory with an arbitrary choice of degree of freedom, then this structure of introducing ghosts will not necessarily lead to a KMS symmetric Lagrangian. And this is at the heart of why some schemes are better than the other, because for some schemes, the ghosts will naturally have be KMS invariant while the others will not. Okay, so this is how you would do it in Schwinger-Keldysh if you wanted to preserve KMS symmetry. This was worked out in a lot of papers that are enlisted here. I'm going to give you a very high level crux, is that for whatever degrees of freedom that you had, the bosonic degrees of freedom, the physical and the noise fields, you introduce an anti-commuting ghost field pair for them, and then you impose that BRST symmetry that we just talked about. But then you close your eyes and you impose by hand a KMS symmetry that takes this particular form. Why? Ask these authors. I'm not qualified to say. But if you impose this KMS symmetry, one nice thing that happens is that this KMS symmetry combined with the BRST symmetry gives rise to an emergent supersymmetry. So not really relevant to what I'm going to say now, but it's a nice structure. The only thing that is important here is that as long as there is a KMS symmetry that my theory is realizing, in addition to the BRST symmetry, I'm fine and I can use that theory to get consistent results. Now, why it is interesting is that once you have supersymmetry, you can actually work with super multiplets and you can actually compute. You don't have to do a functional determinant or some complicated calculation to get the ghost sector. You can actually construct it from scratch using by writing down BRST supersymmetric multiplets. And this is something, again, that can be done. Right now, I am demanding this to be because the thing is, KMS symmetry as a symmetry is technically only defined on the background fields, right? So it's a property of the generating functional, not of the field theory. Psi A is a dynamical field, yes. Why do you say that? Right. Uh, yeah, I think I'm not precisely what you're talking about, but maybe we can talk about that later. So just to give you a short answer, there I mentioned a footnote a while ago that the two KMS symmetries in the two schemes are physically different. So there are actually more than one when the degree of freedom is not conserved, which is the case in model A, then you can have more than one KMS symmetries in your theory. So I think there will be a KMS symmetry that you're talking about, but there will also be this KMS symmetry. And actually, it is this KMS symmetry that you need to for emergent supersymmetry. Otherwise, they will not anti-commute to del partial T. Yeah, so the canonical scheme will actually be invariant under this KMS symmetry as well. Okay, sure. Right. All right, good. So here is my postulated form of the KMS symmetry. I mean, in my world, this is my defining feature that this is what I demand my theory to be invariant under. And then these are the ghost fields, and then there will be an emergent supersymmetry, and everything works out. How everything works out is that you have propagators. You had these bosonic propagators. Now you have a fermionic propagator that has exactly the same retarded pole structure as the bosonic fields, which makes sure that things cancel out nicely. Correspondingly, there is a ghost interaction corresponding to every bosonic interaction. And the way everything works out is that for every such non-unitary diagram that we were talking about, there is a ghost counter diagram that cancels it. This is typically how ghosts work. Once you do that, you can find actually the physical results that you're interested in. You actually get two ghost diagram contributions also for the physical diagrams that we were interested in. And then there are the same three diagrams we had before. You can compute this. I'm not going to give you the computation, but the answers are as follows. You will find that in this case, the grand canonical scheme actually works out just fine. So you have the correct results, whereas the canonical, I mean, I wish I could tell you that this works out irrespective of what scheme you used. It doesn't, to my dismay. But anyway, the canonical scheme that I was talking about, it has all the right symmetries, it has all the right ghost structure, KMS symmetry, supersymmetry, whatsoever. Nonetheless, it doesn't give you the answer that you expect. Whereas if you do that in the grand canonical scheme, it works out. So here is my summary for this last part, is that you can cancel more systematically non-unitary diagrams by introducing BRST ghost fields. Now the BRST symmetry combined with KMS symmetry leads to an emergent supersymmetry in Schwinger-Keldysh EFTs, which you can use to construct these actions bottom up. Hydrostatic compatibility and GGL regularization work differently. So this is my summary. For model A and model B, you will find that basically the roles shift. So the GGL scheme works best with the canonical scheme, whereas the ghosts work best with the grand canonical scheme. So this is to give you the same thing that Thomas had mentioned, that you have to choose the scheme based on the hydrostatic compatibility. You have to choose the scheme based on what correct gives you the correct answers. And in this case, if you want to use the canonical scheme of your action of your field, then you have to use the GGL to give you the correct answers. But if you were to use the grand canonical scheme of your action, Schwinger-Keldysh action, then you have to use ghosts to get the correct answer. Unfortunately, neither prescriptions actually guarantee hydrostatic compatibility. I'm sure there is more structure there, why this is happening. Haven't worked that out yet. So good. Lessons. My lesson number one is that hydrostatic compatibility in Schwinger-Keldysh hydrodynamics is not automatic. So it is the title that I use for the talk is justified, and it depends on what physical representation or what scheme are you using to actually cancel the unphysical non-unitary diagrams that would otherwise appear in your theory. So this could be either GGL prescription or ghost prescriptions. Now, GGL prescription works nice, but it has some formal problems with the unitarity of the symmetric correlation functions that you might or might not care about, but it exists. There may be multiple Schwinger-Keldysh models corresponding to the same classical hydrodynamic model, as we saw. And what fares best with respect to hydrostatic compatibility, the thing that works for both model A and model B in my calculation is a grand canonical scheme. If you use that scheme, which means that you use a hybrid degree of freedom that is related to the chemical potential, then you find that that particular thing works both for model A and B, and in that you can use a BRST ghost prescription to give you the correct answers. Hopefully, this continues to hold when you introduce momentum degrees of freedom and all other things, but that is just wishful thinking. All right, the last one slide, some food for thought. Now, some people might not agree with me, but I have a little bit of hard time to understand what now happens if you tune these series close to the phase transition, especially in model B. So in model A, everything is fine because you can use the canonical scheme and you can use psi directly as a degree of freedom. But in the grand canonical scheme, this is the chemical potential is given by the variation of the free energy, and this term vanishes, which means that the chemical potential is given by a gradient square of your order parameter psi, which means psi becomes a non-local function of mu. So which means if you use mu, or rather that phi degree of freedom that was related to mu as a degree of freedom, then this grand canonical scheme is not really well defined. This puts me in a pickle because the grand canonical, because for model B, the only option I really had with regards to hydrostatic compatibility also was only model B, only the grand canonical scheme. And I am not really sure how to make sense of that here. So some input there will be highly appreciated. And so that sort of brings me to the, like, I don't really have any consistent Schwinger-Keldysh EFT description for model B that works close to the critical point. And if that is so, how does it fit with the conventional stochastic hydrodynamic picture that Thomas was talking about to compute critical exponents near the phase transition? And the second question I would have is that, okay, let's say that the first thing works out, or let's say it doesn't work out and I only work in model A in the canonical scheme. Can I run some real-time Wilsonian RG on these EFTs? So I have this EFT, I start computing renormalization of various coefficients, and I try to find what my UV fixed point is. And for that, you actually need more ingredients than you had before, because right now my theory only had interactions which had at most two noise fields, which is why it's called Gaussian noise. But if you actually take those interactions, you can have these sort of loop diagrams which will generate a 4-point interaction under RG for you. So even if you did not start with a 4 noise interaction, you will generate it under RG, which means that you need, for completeness in your low energy field theory, you need those non-Gaussian terms to have a consistent RG prescription so that you can match with generations like this. And the last one is a little bit more out there, which I'm not sure how many of these you are interested in, but if you want to actually also do a similar distinction, so here I only had two pair of fields, like one noise field, one physical field. Actually, there's a whole extension of Schwinger-Keldysh EFTs where you have out of time ordered correlators, not just retarded and symmetric, which have many, many other fields, not just one R and one A field. They have been known to be related or have something to do with quantum chaos. And the question will be that, can you or do you need to talk about consistent ghost structures there? Instead of n equals to 1, or rather only 2 supercharges, do you get more supercharges? Do you get a higher n emergent supersymmetry? And are there any physical really nice repercussions for quantum chaos? With that, I'll end. Thank you very much for your time, and thanks for the questions. Sorry? Yes, yes. Right, right. My honest answer is I didn't check. I would expect some version of it should still exist if I did dimensional regularization or zeta function regularization. But my honest answer would be that it could very well be that these issues vanish in a more respectable. Right, right. No, as I said, like my honest answer would be I don't know, but at least looking at, I mean, so at some point I decided using this because they were just convenient to do the integrals, but at least at some points in the intermediate calculations, I did see that I don't think that these objects will vanish or like this additional anomalous contributions, anomalous, so to say, will do not seem to vanish even if you use dimensional regularization. But it could be that they actually do. Yeah, I shouldn't say more without doing the computation. Right. I mean, to be honest, uh, at least for this particular problem, you can impose the same cutoff for both frequency and momentum. But the fact that the frequency integrals have a very particular retarded correlation structure, they actually don't end up being cutoff dependent anyway. So even if you put the same cutoff in the frequency space and momentum space, my expectation standing here and thinking out loud would be that it doesn't matter because the frequency integrals are not cutoff dependent. Yeah, yeah, yeah. Dangerous people for me. Yeah. Mm-hmm. 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 I, I would argue we do know what that frame is. This is typically what people call a thermodynamic frame. So it's precisely the frame in which the, I mean, this is defined pretty much from the free energy that it, yeah, right, 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 right. Yeah. I mean, it could be true because, I mean, for me, my free energy is by definition defined order by order in K, right? So my free energy is defined as a perturbative expansion in spatial derivatives. So yes, so I do have to assume some sort of, but I mean, if I want to have finite K effects, I don't think, I mean, I would imagine there is still a non-perturbative free energy, because I would imagine that no matter, I mean, it's not just about hydrodynamics, right? I would imagine that no matter what your complicated field theory that is pretending to describe non-equilibrium phenomena should have the appropriate statistical limit, right? Yeah. Go back to the introduction. Okay. Uh, mhm. So what I'm really meant by, so, so yeah, so statistical field theory, when I say, I really mean just time independent. So basically, I mean free energy. So statistical field theory, by which I mean that you give me a free energy that is independent of time. So it's only dependent on space. Right. Yeah, yeah. I mean, so in general, what you're, yeah, it should be possible to make more than that, I suppose. Right, right, right. So you mean, okay. Okay, I'll really be interested to talk with you. Yeah, thank you very much.